We have finally made it to the end of our Six Sigma and Lean Six Sigma Green Belt course, which is based on the Council for Six Sigma Certification's body of knowledge. If you have not done so already, you should download a copy of the Council's Green Belt Training Manual, which covers the 12th through 24th chapters of their complete study guide. The prerequisite White Belt and Yellow Belt training courses cover the first 11 chapters. The training manual can be downloaded from the course description section for this course for free. But before attempting the 120-question Green Belt certification exam, we should take some time to review what you have learned so far in this training course. Because you will only have 3 chances to pass the exam with a score of 70% or greater in order to receive your dual Six Sigma and Lean Six Sigma Green Belt certificates. This review will take about 5.5 hours to complete and has been split into 3 parts, after which you can take the timed exam whenever it is convenient for you. The last stage of a DMAC project is control. During the control phase, teams build monitors that allow them to ensure that the process continues to work successfully after changes are implemented across the regular business process. At the same time, Six Sigma teams work to transition the process back to the process owner. Up until this point in the DMAC process, Six Sigma teams have worked with statistical analysis tools, and a black belt or other Six Sigma expert has been present to walk team members through analysis and interpretation. While many organizations train process owners and other employees in Six Sigma fundamentals, it isn't always true that a process owner and his or her team will be familiar with the statistical controls that Six Sigma experts have been using. Because of that, appropriate documentation via a control plan and education regarding tools such as control charts might be necessary to ensure business teams can maintain a process and identify when it is out of control and needs remediation. At this time, Six Sigma teams might want to revisit the failure modes and effect analysis. Six Sigma teams initially use the failure modes and effect analysis to identify potential failures in a process and causes for those failures. The failure modes and effect analysis listed potential failure points and ranked them according to severity, occurrence, and detection, calculating a total risk priority number. At the end of the improve phase or beginning of the control phase, Six Sigma teams should revisit the failure modes and effect analysis, noting what recommended actions were completed and recalculating the risk priority number for the improved process. There are 2 reasons for revisiting the failure modes and effect analysis. First, the team is able to see that positive and significant changes have occurred because of the solutions adapted during the improve phase. For any root cause that matched a solution implemented, the team would hope to see a smaller risk priority number. Second, an updated failure modes and effect analysis helps the team identify the next problem or root cause that might be addressed. Remember, Six Sigma is a continuous improvement initiative. The team might have implemented a solution and met an improvement goal, but further improvements can always be made. Control is a time to review the process and suggest possible improvements for future projects. To facilitate continued success, Six Sigma teams should create a written control plan for the process owner. The purpose of a control plan is to help the process owner and business team track and respond to key performance indicators so that the process remains improved. The control plan should be a concise, easy to reference document that tells the business team when to monitor, how to monitor, what range of data is acceptable to the monitor, and how to respond with corrective action if the range measured is not acceptable. Control plans can be spreadsheets, specialized digital documents, or hard copy documents posted at a workstation. A typical control plan includes the company, division, or department name, the name of person who created it, the date the plan was created, the name of the person who last edited the plan, the date the plan was last edited, the project and/or process name or identifier, the process owner, a list of process steps where control actions are required, the critical quality or metric associated with each action required, the limit specifications, or the accepted range of measurements, the unit of measurement, method of measurement, sample size, frequency of measurement, the person responsible for measurement, where the information is recorded, the corrective actions, as well as any associated policy and procedure documents. Note that it is always preferable, when possible, to build corrective action at the process level. This minimizes downtime, puts employees more in control of the process they own, and helps employees stay involved with the quality process. In addition to providing a control plan, Six Sigma teams can implement specific visual controls in a workplace in order to help business teams maintain a controlled process. Visual controls that teams might implement include signs, posted matrices, and instructions, auditing boards that let teams keep track of individual or group performance over time, color coding, and of course, safety signals. Standard operating procedures can often be distilled to visual representation on posters. A coffee shop, for example, might provide employees with a visual representation of what ingredients are used to create various complex drink flavors. Such a poster ensures that employees can prepare drinks quickly while reducing errors in ingredient inclusion. Other standard operating procedure visualizations might include safety procedures in a medical environment, such as visual reminders for hand washing, and short pictorial representations for how to operate equipment, such as hospital beds. In an office environment, pictorial instructions are found on copy machines, where pictures indicate how papers should be loaded, and visual GIFs are often displayed on LED screens to help employees remove jammed paper. These are just some examples that Six Sigma teams can follow when creating documents that will help business staff accept ownership of an improved process and maintain the improvements made. One of the most common methods Six Sigma teams use to monitor a process is known as the control chart. A number of types of control charts exist, and Six Sigma experts must choose the right control chart for the type of data and analytical purpose. A basic control chart is a line chart of data with plot points for specific data points. It has an X-bar line representing the average of the data points, with lines above and below the X-bar line representing 1, 2, and 3 standard deviations from the median in either direction. There is also an upper control limit at the 3 standard deviations above the median, and a lower control limit line at the 3 standard deviations below the median line. Between the various lines, there are areas of the control chart designated as C, B, and A, going in either direction. These distinct areas are important for understanding if a process might be out of control. They are also called zones 1, 2, and 3. A control chart is best displayed using an automated reporting system or dashboard, where process owners or responsible employees can view it as needed. If automated data collection and control charting is not possible, then a business analyst can be tasked with collecting data and presenting it in this format periodically. Though periodic graphical analysis is less likely to catch a problem of control within a process. There are 8 Nelson rules we should follow when reading a control chart. These rules relate to the number, location, and trend of the plots on the chart, and can be used not only to identify potential issues with the process, but also to rectify those issues in many instances. When it is possible to create control charts and display current data on a regular basis, these charts make a good addition to a control plan. Individuals do not have to be well versed in statistical process control to learn about the 8 tests, and business teams with the benefit of control charts can spend more time working on production or correcting issues and less time collecting and documenting measurements. Controlled processes don't have a lot of variation, whereas capable processes also feature outputs centered around customer requirements. When Six Sigma teams deem improvements and the related process to be capable and in control, and they have passed those processes back to the business and process owners, they should take time to celebrate and reflect on the outcome of the project. This is usually done following the final Tollgate review with a sponsor or champion, and can be a quick meeting to close loose ends, recognize the work done by the team, and discuss lessons learned within the process. The celebration and reflection meeting are also a great time for team members to bring up ideas for possible improvement projects. While improvements and the related problems and causes are still fresh on their team's mind, they can effectively brainstorm ideas for next steps. As with any brainstorming session, no idea should be automatically held off the table because it seems silly, would be too hard to implement, is too costly, or seems too big. Not all of the ideas will become future projects, but the team's input provides valuable information that a black belt can later share with Six Sigma leadership panels. After we have completed the control phase and the improved process is up and running, it is time for the last Tollgate review. By the time your team gets to this point, you will have already calculated the performance and capability of the new process. The team will have a written control plan and communicated it to the process owner. A monitor would have been created for the process either through procedures for manual data collection or automated generation of control charts. The team will have provided the process owner and business team with all tools and information required to maintain improvements. As with the completion of every phase, the sponsor or champion must be informed about the state of the improvements and sign off on the project's completion. And, after all of this is done, the team should meet to celebrate the project's completion, reflect upon the project, and generate a list of ideas for future improvements. The team has calculated the control and specification levels based on the data. They have also identified the voice of the customer and the voice of the product levels, which allows them to calculate the overall performance and capability of the newly improved process. A control plan for the newly improved process was created. A monitoring and response plan was also created for the newly improved process. The process owner will be taken over the newly improved process, and it is the Six Sigma team's responsibility to ensure that the owner has the tools and info needed to operate the process and keep it in control. As always, the sponsor or champion must be informed of the process and must sign off on the project completion. To do this, the results of the improvement phase are compiled and presented to the sponsor or champion. The team presents the control methods and shows that they have been put in place. When Six Sigma teams deem improvements and the related process to be capable and in control, and they have passed those processes back to the business and process owner, they should take the time to finally celebrate and reflect upon the outcome of the project. Graphical analysis is a critical part of the Six Sigma approach. Whenever data or ideas can be displayed in a visual format, obvious data trends can be quickly identified and communicated. Visual analysis is extremely helpful when presenting ideas to auxiliary staff or executives who might not be trained in intermediate or advanced statistics. The Black Belt or other Six Sigma experts have the ability to tell the same story that statistics tell, but in a format that can be understood by anyone. Visual depictions are tools that make it easier for Six Sigma professionals or sponsors to retell the story to others, which can be helpful for training, building cultural buy-in for a process change, or even resource requests. From Pareto and run charts to box plots, control charts, and even scatter diagrams, there are countless ways to graphically analyze the data collected throughout the project. As with many other areas of the Six Sigma methodology, it can be easy to go overboard when dealing with graphical analysis, particularly when presenting information to others. With so many tools at your disposal, it is tempting to pick the graph that is new, exciting, or more complex. Often, though, that means spending non-value added time creating one visual tool when an easier tool would do the same job. The simplest graphical analysis isn't always the best choice, though, especially when data elements are not obvious to note. More complex analysis might be required to discover outliers, relationships, and trends. Even when conclusions about data seem obvious, they aren't always correct. This is especially true when dealing with the relationship or correlation between factors in a process. As a Six Sigma expert, it takes time to be able to quickly choose which type of graphical analysis will be best to represent the data at hand. It's also important to note that the best choice for graphical analysis relies equally on the question being asked as much as it does the data itself. While it is true that you don't want to waste time and space presenting data in a way that is not helpful or could be considered muda or overproduction, the same isn't always true when dealing with analysis. At the analysis stage of a DMAC project, black belts and other Six Sigma experts often work with numerous graphical analysis tools as they attempt to understand data. The need to view data in various ways is one reason statistical analysis software is so helpful. Such software takes some of the manual work out of creating these charts and graphs. Trial and error work with all types of Six Sigma analysis tools is also helpful as you learn to identify which tool fits each situation the best. The X-bar control chart plots the mean of a sample over time, or the mean of samples taken over time in the case of an active process. X-bar control charts are one of the most frequently used control charts. Some control charts can be created in Excel using these steps. More advanced control charts require statistical analysis software. To create an X-bar control chart in Excel, we start by creating a spreadsheet with the data points in column A, the upper control limit in column B, the lower control limit in column C, the mean in column D, and the standard deviation in column G1, the upper control limit in cell G2, the lower control limit in cell G3, and the process mean in cell G5. In cell G1, enter the formula equals STDEV and select the data points to calculate the standard deviation of your data set. In cell G5, enter the formula equals average and then select the data points to calculate the mean of the data set. In cell G2, enter the formula equals G5 plus 3 times G1 to calculate an upper control limit that is 3 standard deviations above the mean. Then in cell G3, enter the formula equals G5 minus 3 times G1 to calculate a lower control limit that is 3 standard deviations below the mean. Copy the upper control limit to all the cells in column B, the lower control limit to all the cells in column C, and the mean to all the cells in column D. Then highlight all the data in columns A through D and select Insert, Charts, Line Chart, 2D line chart with markers in order to create a basic control chart. You may also want to add lines for 1 and 2 standard deviations above and below the center line, as well as format the chart to make it easier to read. Nevertheless, the chart can be read and analyzed without any further calculations or formatting. You can complete calculations by hand, but that can be time-consuming and require extremely advanced statistical skill sets. So we will start with manual calculations using the Data Analysis Tool Pack because it helps us to understand the reasoning behind an analysis. But we will also rely heavily on tools that complete most of the calculations for us. Not only does statistical analysis software minimize the time it takes to conduct such an analysis, but it also reduces the chance of calculation errors and increases the accuracy of analysis and conclusions offered by Six Sigma experts. In order to add the Data Analysis Tool Pack, you first select the File tab and choose Options. A dialog will pop up allowing you to select Add-ins, where you will be presented with a list of add-ins both active and deactivated. If the Analysis Tool Pack is deactivated, you can activate it by managing Excel add-ins, where you can select the Analysis Tool Pack and its accompanying Visual Basic scripting, and activating it. Most people already have this feature active in their copy of Excel, and to verify, you can simply choose the Data tab above the ribbon and look for Data Analysis section, which is usually located to the far right of the ribbon. The Analysis Tool Pack is also available in earlier versions of Excel. In 2003 and earlier versions of Excel, you will find the Add-in menu item under Tools. In 2007, the Add-in option is found by selecting the Office button and then Excel Options. In 2010, select File, Options, and Manage Add-ins. Descriptive statistics are numbers used to describe a set of data. Given a set of data about employees in a company, for example, someone might say, over 50% of the employees work in sales or marketing departments. Or they may say, 86% of the employees live in the same zip code that the office is located in. These are descriptive statistics because they simply discuss the nature of the data at hand. Averages, means, and even standard deviations associated with that data are all descriptive in nature. Inferential statistics involve calculations and resulting numbers that draw more general conclusions from the data. For example, if you have data about a sample of 150 employees in a city, not all the employees from a single business, but random employees from different companies, you might be able to use inferential statistics to draw conclusions about the working individuals in that city based on the data in your sample. Descriptive statistics can relate to population data or sample data. Inferential statistics are used to draw conclusions about the population from sample data. If you randomly select 20 people from an overall population and record their height, then the mean of the recorded height is a descriptive statistic about the sample size. Descriptive statistics about the sample are used in calculations for inferential statistics about a population. Probability is the likelihood that a certain event or outcome will occur given a specific set of data or a specific action. If you flip a coin once, the probability of it coming up heads is 1 in 2, or 50%. When discussing basic probability, we talk about outcome and events. The outcome is the result of one trial. You flip the coin once or randomly select a single item from the sample. The event is a specific outcome or outcomes. The coin coming up heads is an event. A person measuring 5 feet tall is an event if you are talking about selecting from a population or sample. While probability measurements can be expressed as a percentage, they are calculated and usually communicated in statistics as a decimal point. Since probabilities are presented as fractions, the lowest probability possible is 0 and the highest is 1. A probability of 0 means an impossible event, and the probability of 1 means a certain event. Six Sigma experts randomly sample the population of all outputs of a process for a certain amount of time. They create descriptive statistics about the sample and use the descriptive statistics to further study and understand the nature of the data they are working with. Once they know the nature of the data, they can work with probability distributions and curves to determine probability via calculations and statistical analysis. Histograms are used to analyze continuous or variable data that is finite in nature or comes from a population sampling. Histograms help Six Sigma experts understand how the spread or distribution of the data is shaped and where the center of that data might be. The center is the average or middle of the data spread, though the mean or median values aren't always located at the center of a histogram. A histogram also shows the range of data, the variation between the highest value of data in the set and the lowest value of data in the set. Finally, the histogram's shape provides information about where the data was concentrated. With the help of the Analysis Tool Pack, we can create histograms right in Excel. In order to do so, we need a table of data, or at least a single column of data points. We also need a bins designation. These should cover the data points from highest to lowest value and should be of equal intervals apart. For example, you could have bins from 10 to 75 in intervals of 5, or a simple count from 10 to 75 by 5s. Once completed, we need to select the Data tab from above the ribbon and choose the Data Analysis tool. When the Tool Pack dialog pops up, select Histogram and click OK. A new dialog box will pop up allowing you to select the data cells for the input range and the bins for the bin range. Select a new worksheet ply and check the box next to Chart Output, and click OK. Excel automatically generates a bin and frequency table as well as a histogram graph in a new worksheet. The histogram design defaults to a standard bar graph, but you can create the look of a histogram by changing one setting on the design. To do this, you need to click on the histogram and a Design tab will appear above the ribbon. You will see an option for Quick Layout, which will allow you to select a formatting option where the bars are stacked tightly together, without any white space in between. Normal distribution, also called Gaussian distribution, is probably the most important distribution related to continuous data from a statistical analysis standpoint. Normal data is shaped symmetrically, surrounding the mean. A normal curve is beneficial for determining the probability that a given data point in a population will fall inside a certain range within the distribution. In a perfect normal distribution, 68.26% of all data points fall within plus or minus 1 standard deviation from the mean. Plus or minus 2 standard deviations from the mean indicates the area under the curve that includes 95.46% of the data points, and plus and minus 3 standard deviations from the mean indicates the portion of the curve that covers 99.73% of the data. Less than 1% of the data will fall under the curve outside of 3 standard deviations on either side. Distributions, even normal distributions, vary a bit. To determine the exact probability of various data points, advanced statistics are required. Excel and other programs perform calculations for you, making it easier to conduct an analysis. Before we discuss probability calculations using Excel, we will look at determining whether your data is normal in the first place. Testing whether data is normal is critical to many steps in statistical analysis, because the results of many tests can be invalid if you do not account for the data you are working with. The chi-squared goodness of fit test takes the number of samples in each bin on the histogram and compares that to the number of samples you might expect to find in each bin given a normal curve. Using the actual number of samples in each bin and the expected number of samples, we can calculate what is called the chi-squared statistic, which lets us calculate a p-value. If the p-value is greater than the alpha risk of 5%, we will accept the null hypothesis that the data is normally distributed. Once you verify that your data is normal, you can use many statistical tests to draw conclusions about the data and the population as a whole from your sample. One of the things that you can do is use Excel's normal probability functions to draw conclusions about the data. To do this, we need a column of data points in any cell, and enter equals NORMDIST, open parentheses, the value you are testing, comma, the average for the sample, comma, the sample's standard deviation, comma, and the cumulative, which can be either true or false, and then close parentheses. If you select true, then the calculation will provide you the probability of selecting a sample whose value is less than the testing value. If you select false, then the calculation will tell you the probability of selecting a sample whose value is the same as or more than the testing value. Six Sigma teams can use Excel to generate a lot of information about the data. Excel also provides a formula for the inverse of the above calculation. The inverse is handled similarly by selecting a cell and entering equals NORMINV, open parentheses, the probability of an event occurring, comma, the mean of your sample, comma, and the standard deviation of the sample, close parentheses. Probability must be entered as a decimal point, not a percent. Then the formula will calculate at which value the probability will occur at. Because we are drawing statistical conclusions from samples, there is some error inherent in the process. Error is usually calculated for in advanced analysis. Correlation and regression are statistical concepts that help Six Sigma teams understand whether two factors within a process are related. You can use these tools to calculate whether an input is related to an output in some way, or even whether two inputs might be related. Strong correlation or regression between two variables does not indicate a causal relationship. Even when strong regression is found between a dependent and independent variable, it doesn't mean that the dependent result is caused by the independent variable. This is a critical concept to understand because attributing causation, because correlation is strong, can mean making poor decisions regarding a process. A team might decide to alter or remove one element because it has a strong correlation to an output. They might then be surprised that the output doesn't change because it wasn't in a causal relationship with the input in question. Nevertheless, correlation and regression are still important to understand because it helps teams understand more about a process, analyze how elements of a process are related, and make predictions about the process. When two elements are strongly related, along a linear line, or even a curved line, teams can create equations linking the two elements together. This lets Six Sigma teams predict how the dependent element will perform if a change is made in the independent variable. It should be noted that the analysis tools don't assume normal data in all cases, but it is possible that very abnormal data can skew results. Before analyzing data, Six Sigma experts should always try to understand what type of data they are working with. Typically, when talking about correlation, we mean the linear association that exists between two variables. Correlation can be strong or weak. It can also be positive or negative. With a positive correlation, when one variable increases, another variable increases. But with a negative correlation, when one variable decreases, the other variable increases. Correlation can sometimes be roughly approximated by viewing a graphical analysis of the data in the form of a scatter diagram or XY plot. If the relationship is strong, you can draw a best fit line through the data points with minimal deviation. Weak correlation is represented on a scatter diagram where a trend line does not seem to exist and where roughly the same number of data points that don't touch the line are located above or below. Typically, the data points located above and below the trend line are somewhat symmetrical, meaning that one side doesn't feature points that are extremely far away from the line as compared to the other side. But this isn't always the case. Weak correlation can be easy to see or more difficult to see on a graph, warranting the use of statistical analysis to make a strong case for correlation. Images aren't always accurate, especially when correlation is weak, and in some cases, an image capturing a small sample could show correlation or no correlation when correlation did exist in the overall sample or data set. Graphical analysis is useful to gain an idea about data relationships, and very useful for illustrating relationships to others. But statistical analysis helps teams to understand relationships with more certainty. For the purpose of correlation, the statistical calculation we are concerned with is known as the correlation coefficient or R value. The correlation coefficient is a number between 1 and -1. As the correlation coefficient approaches either 1 or -1, a relationship between the two variables is considered more likely or stronger. But as the R value gets closer to the 0 point from either direction, the correlation between the variables becomes weaker. Anything under 4% or 0.4 should be considered as not being correlated at all. Once you know that your data has a linear correlation, you can conduct further analysis through regression testing. Regression lets you create a linear model that helps you predict how one variable might behave given changes in the other variable. Note again that the changes are not necessarily an indication of cause, only that the variables are intertwined in some way. When working with regression, we are talking about the coefficient of determination, or the R-squared value. The R-squared value literally is the square of R, or the square of the correlation coefficient. The number tells us about the strength of the linear relationship between the two variables, x and y. While the R value tells us how likely it is that the two values are related in some way, the R-squared value tells us how much the fluctuation in one variable the dependent variable, or y, is related to the changes in another variable, the independent variable, or x. Regression analysis lets us create a best fit line and an equation for our data. And the R2 value tells us how confident we can be in using that line to make predictions about the data. The lower the R value, and thus the lower the R squared value, the harder it becomes to use the data points to make any accurate assumptions or predictions about the future. Correlation and regression are useful tools, usually deployed by teams in the measure, analyze, or improve stages of a DMAC project. The tools don't apply to all data and are not useful in all situations where they might apply. One of the things that a Six Sigma expert develops over time is the ability to decide which tools might be relevant given certain data and situations. Because Excel and other statistical analysis software make it easy for Six Sigma experts and teams to play with data in various graphical and statistical analysis, there is no harm in creating correlation or regression analysis for data to explore connections between variables. This is true as long as you are careful about what conclusions you draw. When in doubt, it is always best to back conclusions up with multiple types of statistical analysis. Both correlation and regression work with continuous or ratio data, and both sets of variables have to be quantitative in nature. For example, you cannot have X variables that are the names of people and Y variables that are the number of outputs. Correlation requires two quantifiable data elements. Regression requires that data can be written as a y equals fx function. Correlation and regression can be applied by Six Sigma experts at a number of points in a DMAC process. During the analyze phase, teams can use these tools to help verify relationships between inputs or to help bolster understanding of root cause analysis. While correlation and regression don't prove causation, they don't negate causation either. A strong correlation doesn't prove causation, but if a team already believes causation is a factor, then a strong regression model helps validate that assumption. This is especially true if teams couple regression modeling with trial and error hypothesis testing. While it is true that the normal probability curve is the most important and commonly used distribution in statistics and by Six Sigma teams, it is also true that every set of data is not going to fall along the normal probability distribution. Sometimes outliers can cause your data to become skewed to the left or to the right. Other times, multiple distributions may become combined in your data, giving the appearance of a bimodal or multimodal distribution. You may also have issues with insufficient data, which can cause a normal distribution to look completely scattered. In the end, make sure that your data is appropriately graphed. That is, make sure that you are graphing your data on the appropriately labeled axes.